or good morning or afternoon as the case may be. I'm going to be looking at digital filters, but this isn't a in-depth study of digital filters because that would really take too long. I just want to give a reasonably brief idea to those of you that want to add, say, something simple like a low-pass filter to some sequential code in C or something that you're working on. And you know the sampling rate, and you want a low-pass filter. So a low-pass filter, if you remember, is in analog would look something like this. This is the simplest form, the first order. Of course, we get second order and we get Butterworths and Chebyshevs and all this, but we don't need to go to that level of detail at the moment. And we need its transfer function. Oops, this delete there. So we need its transfer function. So V out over V in, if you do the sums here, we can write it in Laplace form as 1 over 1 plus ST. That's the commonest form, where T is CR. And you get that because this is a voltage divider of Vn, the capacitor, and it's got an impedance of 1 upon SC, or 1 upon 1 plus j omega C, and R, and when you do the sums, you get that. You can also write it in j omega form. It's 1 over 1 plus j omega T, where S, of course, is equal to j omega. And the cutoff of the filter, we call omega C, is equal to 1 over the time constant, which the time constant is C times R. And therefore, if we just continue this, we can write that as 1 over 1 plus j omega over omega C. So that's yet another way to write the transfer function. Or we can write it as, because omega is equal to 2 pi times the frequency, f, we can write it as 1 over 1 plus j, and the 2 pi's are going to cancel out anyway, f over fc. Okay, so that's sort of 3 ways you can write the transfer function. This is sort of preferred by many electrical engineers. The S domain is control systems people, and some people use omega as well. And if you remind yourselves of what the Bode plot looks like, when f is equal to 0 here, there's no gain in the system, so the gain is 0 d. Well, there's a gain, it's unity gain. When f is 0, that disappears. And 20 logs of the base 1 is 0, so it's 0 dB of gain at low frequencies. And asymptotically, the plot just is flat, and then it goes down as a slope of minus 20 dB per decade. And you can work decade as a multiple of frequency of 10 times. So, for example, 1 hertz to 10 hertz, or 10 hertz to 100 hertz, that's a decade. Or you can do the same in radians. So that particular cutoff frequency is, in radians, it's 1 upon t. Or you can do the same thing and write it in hertz. If you want to do this, it's just the same plot with a different scale. Oops. And that's going to be f cutoff equals 1 upon 2 pi t. Notice that 2 pi, so be careful if you're dealing in hertz, which we usually do, of course. It makes the most sense to deal in hertz. But control engineering courses tend to do everything in radians for some reason. It just saves having to put the t in there. So anyway, there's a whole load of things we can use in control systems. We could have, for example, a lag filter. You may have come across that, phase lag, which is a sort of poor man's integrator, really, without, well, it's not got any gain in it. That would be like R2, R1, and C. We could have a phase lead. Sorry, that is a phase lead. Sorry. That's a phase lead. We can have a phase lag, which is this one, like R1, C1, R2. And combinations thereof, or we can have active filters if they're first order. I'm only going to be looking at very simple filters here. I'm not looking at Butterworth filters, and although we can do that quite easily once we understand the basic theory. So this is a first order filter, or if you can, an analog one, that sort of R1 just for the DC, so it's the same currents going in both of these. That would be R2, and that would be a C. V out over V in. If you take the transfer function of that guy, you get V out over V in. It's also first order. We can write that as K over 1 plus ST, where again K is equal to R2 over R1. Actually, there's a minus sign there. It inverts because it's an inverting amplifier, but I'm not worried about the inverting sign for the moment. And T is equal to CR2 in this case. Okay, so these are analog filters, but how do we get to the digital equivalent? We've got a piece of software. We obviously can't put these circuits in there. And in the old days, of course, we could. But now we've got everything in software. How do we put them on software? So there's quite a theory behind this, going back to Shannon's sampling theory. It was a bit more than Shannon that designed it. He's the most famous electrical engineer, of course, but there were Kalashnikov and a few others, a Russian engineer, and even a mathematician called Whittaker in Edinburgh University. I think it's a statistician, originally came up with the theory, but for electrical engineers, it's usually called the Shannon theory. And that tells us that we have to sample, to digitize something, at least twice the bandwidth of the signal that we're dealing with, or greater than twice. And usually twice isn't enough. We usually do 3 to 4 times or whatever to get a little bit more resolution. Sometimes it causes problems even if you follow the sampling rule and you don't sample high enough. So I'm going to assume that kind of knowledge is already with you, and we know how to sample, and you know what steps to take that you've got to be careful of a thing called aliasing, because that would take me far too long to look at all this. That would be in other lectures. You need to go on a whole course on this. So I'm going to jump now to assume that you know that bit. And we're going to move to, instead of Laplace transform, it's going to move to the Z transform. But we needn't be scared of the Z transform, because in this particular case, I'm only going to use it for one thing. I'm not going to be going into complicated Z transfer functions and step responses and all the sort of stuff that you'll see in textbooks. It's going to be a much simpler approach to this. And the Z transform is the sort of digital version of the Laplace transform. So the Laplace transform S and the Z transform Z. So just as in with you get a transfer function in S, you can get a transfer function in Z. So we'll come to that in a minute, but the relationship between the two is as follows. From the Shannon theory, Z is equal to exponential ST, and I'll call that TS. TS is the sampling frequency. Whatever you've chosen it to be. So I'm assuming you've chosen a proper sampling frequency. So the sampling, that's not the sampling frequency, that's the sampling time, that's the sampling interval. The sampling frequency is reciprocal of that. So the sampling frequency is 1 upon the period. So that's the sampling frequency in hertz. So for example, if you wanted to sample at 10 kilohertz, we can work out the sampling interval as 1 over 10,000 or 100 microseconds. So if if the sampling frequency was 10 kilohertz, TS would be 100 microseconds, 1 over 10,000. Okay, so, but that is the basic relationship between the two, between the so-called Z domain and the S domain. And the problem with that is this exponential term here. I mean, you can see straight away if you take logs of that, you get log Z is equal to STS, and therefore S is equal to log Z over TS. And if you look on Wikipedia and a few other sources, you'll see that people derive approximations to S from Z and the other way around using from log really. And you can do that, and that's probably a good way to do it. But I'm going to use a different method. I'm going to use a Taylor series. So you don't need to understand all the ins and outs. The answer is quite simple once we've done all this. But going back to Z is equal to exponential ST, clearly we can't use that because logarithms are sort of multi-valued function. What we could do is we could expand e to the ST, and if you know your Taylor series or Maclaurin series, it actually is, you can show that that's equal to 1 plus ST plus S squared T squared over 2 factorial plus so on. And I'm only going to take the first term. So I'm going to say Z then is approximately equal to 1 plus ST. And then I'll rearrange it and say that S then therefore is approximately equal to Z minus 1 over T. So now I've got a relationship between my Z domain thing, which I'll talk about in a minute. You might think, well, what's he getting things into the Z domain for? Well, I'll talk about that in a minute. Actually, that should be TS, shouldn't it? Not T. So it's TS squared and so on. So that would be one approximation. So that's only an approximation. That one is called the Euler or Euler approximation. It's one of Euler's one. There's another one as well. You can say Z is equal to 1 over e to the minus ST, can't you? Or STS it should be, which is the same as e to the ST. And that's approximately equal to 1. Again, we can do an expansion of a 1 minus STS plus and take the higher order terms. But if I just ignore the higher order terms and just take the first order approximation and I rearrange it, I'll find that S is approximately equal to Z minus 1 over ZTS this time. So very similar to what we had before, where there's a Z term there. So this is Euler's approximation again, but it's a second, like a second, another approximation. We can look in more detail. It's some later point, or you can look in more detail in a textbook as to why you use one versus the other. But we're not going to use any of these. We're going to use a better method, and I'll explain why it's better in a minute. But let's go back to Z is equal to e to the ST, e to the STS, and we'll write that as e to the S TS over 2. A lot of people don't like you doing this because they say it pre-assumes you know what the answer is to do this, and you should use the log method, and that's fine, but it's not so easy to understand perhaps. So I've got e to the S t upon 2, e to the minus S t upon 2, and that's equal to e to the ST. And if I expand the numerator and denominator now, I can say that's approximately equal to 1 plus STS over 2 over 1 minus STS over 2. And now if I rearrange that, I get that S is approximately equal to 2 over sampling interval Z minus 1 over Z plus 1. And that's the one I use all the time. That's called the, there's two methods, it's two names. It's called the trapezoidal method, and it's also called Tustin's method. And what's actually happening here, though it's not kind of obvious, is it's similar things to what you might have studied when you do basic calculus and you're trying to find the area under a curve, which is basic calculus really. So you've got some kind of curve and here, like f of x versus x or something like that. And you want to find numerically what the area, of course you can use calculus if you know what the expression is, but numerically, how do we do it? I'm just going to take, divide it up into chunks, and each one of these is like the sampling interval. But if I zoom in on one of these, just zoom in on one of them, let's just take one of them and I've expanded it. So suppose it looks like that. That's my sort of present sample here, and that's my next sample. I can see straight away that if I'm going to work out the area under there, what I'd have to do is work out that area and then the next one and the next one and add them all up. But how do I do it? I could, for example, do this. Okay. Now, if you do that, that's approximating the area to a rectangle. And it's known as rectangular integration. And there's two versions of that, and this is really the Euler, what the Euler method is. Okay, but the better way to do it is to go back to it again and approximate the area as a trapezium, like this. Then because here you're missing out that bit there, aren't you? You think about it. So here you've got a trapezium. So that's a trapezoidal integration. And I know this is very brief, but you can sort of, say, dot the I's and cross the T's later, really. So it turns out, again, without going into all the maths, that this trapezoidal method is a better approximation than the rectangular methods, although you can use the rectangular methods for certain applications. There's no question about that. We use them just as basic integrators, for example. But the trapezoidal one is kind of better. It has its own problems as well, in that to get accurate results, you need to sample about 10 times higher than the sort of highest frequency of interest that you're going to convert from analog to digital with. Otherwise, you get a phenomenon known as frequency warping, but there's a way around that called frequency pre-warping. But anyway, in control systems, we usually sample about 10 times higher anyway for other reasons, because there's an inherent delay in a digital control loop. It's a one-step delay. You can't get around that. It's a minimum of a one-step delay. Of course, there could be more delays as well, but it's a minimum of a one-step delay. And that any time delays within a negative feedback control loop causes instability. So we're going to use this approximation. S is approximately equal to 2 over the sampling interval, z minus 1 over z plus 1. So we're just going to use a straight substitution and use that. And as I say, the fine details you can figure out at a later date. But how is that going to help us? What that'll do is, so for example, we've got our transfer function g of s. So 1 over 1 plus st, not ts, that's just a time constant. Now what we'll do then is we'll substitute s is equal to 2 over ts, z minus 1 over z plus 1 into that. And what that'll give us now is a transfer function in z, or z, depending how you want to pronounce it. So let's do that without, try to do it a bit briefly. So you get 1 plus t times, and then you substitute the s bit. And of course, you can do this for any transfer function you like. So it could be second order, third order, fourth order. Of course, it goes without saying that the higher order, the more difficult the algebra is. And because of that, there's a command in MATLAB called bilinear, which if you've got MATLAB, I realize not everybody's got MATLAB. So this talk isn't just for students, it's for people who want to make simple filters in their programs. So anyway, how do we simplify that? It's basic algebra. We can just multiply by z plus 1 the numerator, and then we get z plus 1 in the denominator, plus 2 t over ts, z minus 1. Then what you want to do is you want to collect the terms together. Then z, so the numerator is easy, it's z plus 1 then you're going to get z into, well, what is it, 1 plus 2t over ts plus 1 minus 2t over ts. So that's the same variable there, the 2t over ts, so that's handy. But what I'm going to do now is take out this bit and write it as z plus 1 over 1 plus 2t over ts, and that gives me z plus, and then it's 1 minus 2t over ts over. So it does take a little bit of algebraic messing around, I'm afraid, to do that. It's worse, of course, for second order. And that's my answer. What I really want to do is have a 1 here in front of the z bit, for reasons that will become a variable, obvious in a moment. But so I can define some variables now. I can say this is equal to k z plus 1, k is a constant, over z plus a, okay, where k is equal to 1 over this guy here, 1 plus 2 ts over t, okay, and a is equal to 1 minus 2t over ts. That's the sampling interval, or 1 plus 2t over ts. So I need to do this in my program as well. So I need to know the t, of course, for this cutoff frequency, because I know the frequency of the cutoff is 1 over 2 pi t. So therefore t is equal to 1 over 2 pi fc. So I must select fc because that's my cutoff frequency. So what it can be, 20 hertz, 30 hertz, 100 hertz. This is just a low pass filter, remember. I'm not doing anything more complicated. Then that gets me t. Ts I know because it's my sampling rate. I've defined it in the program. So if I know t and I know ts, I know a, and I know k now, so I've got everything. So we can write it as g of z is equal to k z plus 1 over z plus a, and that gives me a z transfer function. But how does that help me in getting a digital filter? So this is like the first stage, is I convert from g of s to g of z, and so that's my first thing, and I do it with the bilinear transform because it gives me more accurate results. The other thing is if you have a transfer function it's stable in analog, most of them are stable if you're designing something, then you expect it to be stable in the digital domain. Otherwise, if it's not stable, it's pretty useless. It means the output just sort of saturates, just goes up to a huge number. So whatever, for a stable analog, you must get a stable digital system. And this one guarantees it, the bilinear method, whereas the other methods do not guarantee it. So that's why I say use this method if you're going to convert from S to Z. There are other methods as well, pole zero mapping method, impulse invariant method, and there's sort of a few others, and again, they're all lectures in their own right. So I'm going to write this in what's called the backward form, just by writing it as in negative terms of powers of z. Okay, so it's like I've divided the numerator and denominator by z. So I get 1 there, and I get 1 over z, which is z to the minus 1. 1 plus a over z is that. Okay, so why have I written it like that? Well, I've written it like that because if I go back to my original expression, z is equal to exponential sts. If I write it in negative form, this is recognizable if you know your control system as a time delay. Okay, it's a pure time delay actually. And if you either have, you haven't studied this, but it's a time delay of ts seconds. Now ts is is the sampling interval, which is really nice. In other words, it's just like one sampling interval. So z to the minus 1 can be interpreted here as a one-step time delay. Of one sample. Likewise, if you had a higher order filter, z to the minus 2 would be two-step delay, and z to minus 3 would be 3 steps, and so on. You can see z as, and rather than z to the minus 1 as being the opposite, as being one step ahead in time, but it kind of makes more sense to have a delay than something going into the future, but you can actually write it that way as well if you want to. Okay, so what that means is that if we've got a discrete signal, and how do we write a discrete signal? Well, how do we write an analog signal? A discrete signal means sampled signal. So an analog signal is written as, say, y of t in functions of time. A discrete signal is written as y of, either written as y of k, or it could be written y subscript k. You don't usually use superscript. So it's that one or that one, where k is an integer, 0, 1, 2, 3, 4, and so on. That's the sampling interval. So in other words, y at time 0 means means a signal at time 0. Y at time 1 means a signal at sample interval 1. Y at 2 means sample interval 2. In actual fact, it should be y at 0, y at ts, y at 2ts, and so on. But we normally ignore the ts and just make it easy because we know ts is there anyway, sort of thing. So we don't bother. So often, initially you might write that kts or y of kts, but what's the point in putting the ts there all the time? We just leave it out, and it just becomes y of k then at each sampling interval. So if that is a discrete signal, a sampled signal, then we can write that z to the minus 1 that operating on it, I'm going to write it in subscript form, shifts it backwards in time. So we write it as yk minus 1. So likewise, if you had a second order delay, z to the minus 2, that would be shifted back 2 steps in time, and so on, 3 and 4. And if you wanted to, you could say z times y of k is equal to y of k plus 1. It goes forwards, the opposite. Z goes forward, z to the minus 1 goes back. So why am I telling you this? Well, because we can get a transfer function now instead of in the analog, instead of in terms of Laplace, we can kind of skip a step and go to the time domain directly and cheat a little bit and say that if we've got a transfer function g of z, we can write it g to the minus 1 if you like, g of z to the minus 1. We can write it as y of k over, say, u of k. Although that's mixing frequency and time, it's kind of done all the time anyway. So here's my transfer function g of z, or z to the minus 1. I've got an output y of k, that's my filter, and an input u of k. So back to our, so we can do that for any so-called linear time invariant transfer function. We can do that. It doesn't matter what the order is, and we can cascade them. So, for example, if you're designing a first order filter, we could get a second order filter by putting two next in cascade. So you could have like G1 and then G2, just like you do in the analog domain. You can do the same in the digital domain as well. So you can then make a higher order filter from two. Except for these would be software, of course, and rather than hardware. You don't get the buffering problem that you do in software that you do in hardware. So if, for example, if you in analog were to put two first order filters that weren't buffered, there was this, in other words, the output impedance here isn't 0 when you connect them. you don't get, so this one is 1 over 1 plus st, say. This is 1 over 1 plus st. And you connect them together, you do not get 1 over 1 plus st squared. So that's a fact. But you would if they were buffered. But in software, you don't have that problem, which is rather nice. So you can just stick them together because there's just no loading problems exist. So my transfer function, either I can write it z to the minus 1 or z, was k z plus 1 over z plus a, where I defined the variables earlier. Oh, sorry, I should have written it in backward form. It's 1 plus z to the minus 1 over 1 plus a z to the minus 1. Okay, I think I did that somewhere, I hope. Oh yeah, here. Okay. So I'll go back to that. And now sort of draw that in a box to show that it's our transfer function. So although this looks complicated, once you kind of know all the steps, it's pretty straightforward. So we can say y of k is equal to k 1 plus z to the minus 1, and we just multiply them out. And as to say, if you're a purist, you wouldn't like this because you're mixing frequency domain and time domain quantities. But nevertheless, engineers break lots of rules and get away with it. Mathematicians would have a fit. So what the mathematicians normally do is they use q to the minus 1 if you're writing formal papers, and you call that the shift operator. But really the thing it just means you, instead of using a z, you use a q, and the thing's exactly the same. So a lot of us think, well, why are we even bothering? So I'm going to cross multiply and I get yk. So this is using z as an operator anyway. It's called an operator. So from that transfer function, you can see we get this. And then remember what we said earlier, that z to the minus 1 shifts a signal back in time by one step. We get y of k when we multiply that one out. And then we multiply this, we get a, y. Now the z to the minus 1 shifts it backward in time. And this gives us k, obviously u of k, plus k, and the z to the minus 1 is going to shift it backwards in time. This is called a finite difference equation, and this is what I'm looking for. Don't be put off, it's just something you've got to learn. Finite difference equation, it's the first order one because it's only got one pass value of y. If it had k minus 1, k minus 2 would be a second order. This is the analogy, if you were to do the continuous time over here, you would have a differential equation describing a circuit. If you had an analog circuit, you can write the differential equation. I'm not going to do that, but you can write the differential equation of that circuit, and then you could take Laplace transforms if you wanted to. But in discrete domain, you don't have differential equations. You have difference equations. Okay, so you need to learn the difference. But you always write it with the output. You don't write yk plus a yk minus 1. We write it with the output on the left-hand side and the input to the right. So y of k equals minus a yk minus 1 plus ku k plus ku k minus 1. And that's it. And that's what I'm going to implement in software. And it takes, I know it's taken a long time, but it would take even longer, believe me, if we went into the details of the sampling theorem and all the ins and outs of it, it would be like 3 or 4 lectures or something. So I'm assuming I know what A is and I know what K is because I worked them out earlier. So how do I go about writing this in software is the next problem. And what actually is it? What is a difference equation? So this is important. That's the current output. I don't mean current as in amps. It just means the current as in the present output. That's the last output because it's one step behind. This is the input. That's the present input, and this is the past input. Okay, present input, past input, current output, and the last output, or the previous, we can say previous, if you like, previous output. So it means that if you've got data going in, as you use the input, you need y as the output. And how do I implement that in some sort of code? Well, as you know, that you could do all sorts of things. You could use arrays. You don't need an array, but you could. There's a host of different ways of doing it. But the easiest way by far for something simple, I'm not saying you're going to use this for something, you know, a very high order filter, but for a simple filter, is to say let u of k be defined in your code as, I just call it, say, u0, and uk minus 1 as u1, and then I kind of adopt that notation, so I can say yk is represented as y times 0. That's the current output, and yk minus 1 is y1. And if I had a k minus 2, I just write it as y2. Okay. So what I'm trying to implement is this guy up here, yk is equal to a, yk minus 1. So to implement in the software, all I need to do is say, well, I need to, u2 is equal to u1, and then u0 is equal to, and then I need to read the input from somewhere. Okay, I don't know where it's coming from, but I'm going to read it. It could be from, let's say, outside in the analog world. You could read it from the analog to digital converter. It could be a sample that you know, from another piece of software, or it could be from a digital sensor, so it's already in digital format. You don't have to read it in. So this is called shuffling. So I mean, if this is in C, you'd have to put your semicolons and everything. I call that shuffling, and this is because it's a past value. You're kind of shuffling. You're saying that, oh, U2 is equal to. I don't actually have a U2, do I? I've just realised I made a bit of a mistake there. Sorry about that. So it should be U1 is equal to U0. Sorry. U1 is equal to U0, U0 is equal to that. If I did have a U2, however, it would be U2 is equal to U1, U1 is equal to U0, U0 equals, then you read that. And you do the same with the Y. So if there's a Y2, but there isn't one, you do that first. So Y1 is equal to Y0, and then Y0. And now we know, look at the difference equation. It's equal to minus a, well, assume we've defined a up at the top of the program, minus a times y times k minus 1 plus k, and again, assume we know what k is, times u at time k, which is u0, plus k times u at time 1. And, you know, you can put a semicolon again if you wanted to, that. And then we output y0. So that is our digital filter here. So this is a digital low pass filter with the cutoff defined earlier. So all the parameters were worked out earlier. I think we did it here. Where was it? Way back here. Oh yeah, we did it here. K was equal to that. A was equal to that. That's all we need really. So, and we know the sampling frequency, so we know the sampling interval because you define it in the program. And so we know what A is, we know what K is. But how does this actually link into a real program? So let's see if I can swap the screens now. This is going to be interesting to see if it works. Capture the main screen. So we're back to the main screen now. So see if it can see. I'm going to make it do the second screen. So many screens here. Here we go. Now I hope you can see this because it looks a bit small on my screen. So this is my DC motor servo thing that I was writing, and I've got on YouTube showing you how to control it. So what I've done here, if you look at the definitions, I've defined float as real values, sampling interval TS. I don't really need the sampling frequency because I kind of know the sampling interval, but I don't know, I think I used that earlier. That's the cutoff of my filter. That's the time constant of my filter. That's the K term, I just called it KZ. That's the A term, AZ, and I've got another term called BZ. And instead of Y0 and Y1, I had trouble using them because it's, I don't know what it was reserved or something. I called it YA0, YA1, and U0, U1, and I need pi as well. Now, if you remember the sampling, I can. So in your software, you need to declare the sampling interval. I've declared it as 10 kilohertz. So it's in this bit of code here is unsigned long. Previous time equals micros, and then the time, that's the defining the previous time rather, and the time interval is 100 microseconds. It's going to be 100. It's going to be used later. So if I wanted a different sampling interval, I could change that. That's 100 microseconds. The actual loop itself, there's the void loop. So that's our main loop that we're doing the PID controller in. Current time, it gets the current time in microseconds. If the current time minus the previous time is greater than the time interval, then it does the PID control. So that's working out the error. Then it does the PID bit. So it just works out the error is the set point. That's counter 2 minus the actual motor output, which is they're both counters, and so these are both integers. It gives me the error. So I need the error, obviously, if it's a servo. Then I take I differentiate it. The differentiation is, I should really divide by t, the sampling interval, but for reasons explained in a minute, I don't need to do that. Then this is an integrator. This is also a difference equation, I error old equals I error. But the bit that we added is here. This is the first order filter, the bit I've just been mentioning. So because I've got the output of my PID controller is the error times Kp plus the differential, or the difference of the error times Kd plus the integral of the error times Ki. If I want to filter that now with a low pass filter, that is now my input to the filter, this thing called control. That's variable float control. So U1 equals U0, I mentioned that. U0 equals the input, well, that's a control, that's from the previous software. Then the output, Y, I said Y1 equals Y0, but it's YA1 here, Y0, and Y0 is equal to that. It's my difference equation. And then I output Y0, but it's going to the PWM channel. It's got to be the absolute value because the sign is taken care of in another part of the program. So that's that just goes to pulse width modulation. That's just to stop it doing daft things. The output. Sometimes, the best efforts, it still doesn't work, and you need to just stop it going to silly numbers, because when you've got an integrator in there, there's a problem. So that's how you go about implementing a low-pass filter. But I just want to go back to the other screen. So there should be a screen 3. Did it take that one away. So why is it not showing? Right. So we're back to the other screen. So just a few more things before I finish off. I did mention that there was other methods, the Euler method and so on. If I want to implement an integrator like in a PID controller, we usually don't need to use the trapezoidal integrator. You can use it if you like. We usually just use the Euler integrator. So for example, I said that one of the approximations we had was that S is approximately equal to Z minus 1 over T. That was the Euler method. And we usually use this for integrators because, so that's a differentiator. We can write it in backward shift, if you like, as 1 minus Z to the minus 1, or as a Z to the minus 1 at the input. But that's an integrator. It's reciprocal. 1 upon S is equal to, or approximately equal to T over Z minus 1, or Z to the minus 1 T over 1 minus Z to the minus, actually that should be TS, I'm sorry, the sampling interval, over 1 minus Z to the minus 1. Okay, write it like that. So our integrator in analog form is that, and in digital form it's Z to the minus 1 TS over 1 minus that. At least that's one form of integrator. And then the other form, the second Euler one, doesn't have the Z to the minus 1 in there. That's a delay. And actually that's I think the one that we're going to use, not this one. So we're going to use the one with the Z on the denominator. So an integrator, a simple integrator, just let's use the other form first of all. So 1 upon S is approximately equal to, then the other integrator form was Z minus 1 over ZTS. That's the second Euler form. And sorry, that's S is equal to that. So 1 upon S, the integrator is equal to ZTS over Z minus 1, or that's also approximately equal to TS over 1 minus Z to the minus 1. That's even simpler still because there's no Z to the minus 1. So if we write that as like that, and then we have Y is the output and U is the input, we can implement an integrator very easily, do the same kind of thing as before. Y of K is equal to TS 1 minus Z to the minus 1 U of K. That's just writing, that's what a definition of a transfer function is. Output equals the transfer function times the input. You get Y of K times 1 minus Z to the minus 1 is TS UK. So that we get, using this backward shift, we get YK minus 1 equals TS times UK. So therefore an integrator, an Euler integrator is Y of K equals YK minus 1 plus TS times UK. So that's a Euler integrator. And that's the one that's used in most PID algorithms, or simple PID algorithms. The TS, you might have seen, so what it is, like the present output is the past output plus sampling interval times the input. But you might have noticed in my code I don't put that there. The reason is because if you're multiplying that by a gain, an integrator gain, so in other words, if the transfer function is Ki, instead of this, it's Ki, where you've got integral time constants, the Ki and the TS then become multiplied together, don't they? So you have YK is equal to YK minus 1 plus Ki TS UK. And really there's not much point in putting TS, because when you multiply it by Ki, you're going to get a new constant, which we call Ki dashed, let's say, or whatever. And so you might as well just miss it out and call it Ki the first time round. And so you can implement an integrator with a gain term as just that, Ki UK. So that's an integrator. And you can show that's actually equal to a summation as well if you want to, because well, you think it is actually adding because it's taken the previous value sample and it's summing up forever really. So that's an integration for a difference term, a differentiator, S, that sort of Euler differentiation. You can again go back up and see that Here's, well, I suppose we could use that one, or we could use, use that one. It's the same one we're using again, z minus 1 over zt. So S is a differentiator, so Z is approximately equal to Z minus 1 over ZTS, which is, writing it in backward form, it's 1 minus Z to the minus 1 over, divide the numerator by Z, denominator disappears. You get that. And then when you implement the differentiator, actually what's going in is usually the error, of course, but I'm calling it U of k here, but it's if it's a PID controller, it's usually the error that's going in to that bit. Sorry, get rid of that. Then we get y of k is equal to 1 minus z to the minus 1 over ts u of k, and that is just purely 1 upon ts times, when you multiply uk, and then that becomes uk minus 1, so it's just uk minus 1. So that's just a difference. The first difference, so differentiation is just a difference. And again, it's multiplied by this thing here, which is a 1 over the sampling interval. But if we have a gain term in the differential, which is kd, then you end up with kd being here, and then kd goes there. So again, you've got a new constant kd over ks, which you might as well just redefine as kd. It makes no difference. I mean, you can leave it if you want to be accurate as kd over ks, but it just means the numbers are different scalings, that's all. You can, those two are absorbed. So that's a difference term. An integrator was, this is an integrator, that's a difference. You just take and it would be the error minus the previous error. For integrator, it would be output is equal to the previous output plus ki times the error. Again, they're all going into the error. And the proportional term is just a multiplication by a scaling factor. So that's why when I go back here to the second screen, I hope you can see that. I don't think it's not showing up, is it? I wonder why the second screen's not showing. Capture main screen. It's strange. I'll go back to the first screen then, so you can see it there. So the PID part is here. So these are the gains which I found by sort of tuning method. We're finding the error. It's just the counter 2 minus counter 1, and then differentiates just taking the difference. So integral, so this is like our integrator, the output is equal to the previous output plus ki times the error. So you need to shuffle the outputs as well. So say the old error, or the integral of the old error is equal to the integral of the error, and then there's a new one there. And then you just add them all together. Error times kp plus difference of the error times kd plus integral of the error times ki. That gives you the control. And then you pass that into your digital filter if you want the derivative action. I hope you can see that. So that's about it then. It's very brief. I'm sorry it's a bit short, but if you want more details, you need to sort of attend some lectures, or maybe there might be some in textbooks or online. Thank you very much for watching.